Neural networks from scratch in pure Python. No autograd, no framework, no magic. Standard library only, and code you can read from top to bottom. If you followed the inductive biases series, this is the debt it kept deferring. How the gradients actually flow is its own series, and you are watching it. So here is the whole premise stripped bare. A neural network is nothing but a parameterized function. You hand it some numbers, it hands you some numbers back. And the smallest version worth training is a single straight line.
A single line that barely sounds like a network at all.
It is where everything begins, and every larger network is just many of these stacked up. In our code, it is one layer, a linear layer with two inputs and one output. Two numbers in, one number out. Look at what it computes. The forward method is a single line. It takes the dot product of the weights with the input and adds the bias. Set as an equation, the score equals the weights times the input plus the symbol b. That score is the raw output of the unit, and we will call it the logit. Let us open it up. What does parameterized actually mean here? For two inputs, this unit holds exactly two weights and one bias. Three numbers, and those three numbers are the entire model. The dot product is just this, the first weight times the first input plus the second weight times the second input. Add the bias, and you have the score. Training is nothing more than searching for the three numbers that make that score come out right, again and again, across all of the data. Feed this unit a point in the plane, and it returns one score. Higher on one side of a line, lower on the other, and exactly zero right along it. But a raw score is not a decision. A line, all by itself, is not yet a classifier. To make it actually decide, we have to bolt something onto the end of it. A line hands us a raw score, any real number at all, from far below zero to far above it. To turn that into a yes or a no, we attach a head. Ours is called sigmoid BCE. A sigmoid, followed by binary cross-entropy. The sigmoid does the squashing, the cross-entropy does the scoring. Two small jobs, one head.
Why a sigmoid in particular? Why not just threshold the score at zero?
Because we want more than a hard yes or no, we want a probability. And a probability has to live between 0 and 1. The sigmoid bends the entire number line into that interval. A large positive score comes out near 1, a large negative score near 0, and a score of exactly 0 lands right at 1/2. In the code, the prediction is a single line, the sigmoid of the logit. That number is the model's confidence that this point belongs to class 1. Now the second job, scoring that confidence against the truth. That is what binary cross-entropy does. If the true label is 1 and you confidently said 1, your surprise is tiny. If the truth is 1 and you confidently said 0, your surprise is enormous. The code computes this straight from the logit in a form that never overflows, but the meaning is simple. It is how surprised the model should be at the correct answer. That surprise is the loss. Better guesses make it smaller. This split is the spine of the whole series. The body computes numbers, the head decides what those numbers mean. Swap the head and the very same line becomes a different model. A counter, a real valued predictor, a many-way classifier. But for now, we have exactly one question left, and it is the only one that matters. How do we make the loss smaller? So how does a wrong model become a right one? Not in one clever leap, and not by solving any equation. By a loop and a surprisingly short one. This is the beating heart of the fit method, the part that actually does the learning. Everything else in the library is scaffolding around these few lines. For every small batch of examples, it runs the very same 4 steps, over and over, epoch after epoch, until the loss stops falling.
4 steps, walk me through them slowly.
Step 1, forward. Push the input through the layers and read off the score. Step 2, loss. Measure how wrong that score was against the true label. Step 3, backward. Send that error back through the layers and find each weight's share of the blame. Step 4, step. Nudge every weight a little, in the direction that lowers the loss. Forward loss, backward step. That sequence repeated is the entire training engine. One detail before each batch, we zero the gradients. The backward pass adds up each weight's blame across the whole batch, so we have to wipe the slate clean first, or this batch inherits the last one's mistakes. Then we run forward and backward over every example, letting the blame accumulate, and only then take one step using the average. Clean the slate, gather the evidence, take one step. That is the rhythm. And the step itself is humble arithmetic. Each weight slides downhill by a small fraction of its gradient, that fraction being the learning rate averaged over the batch. That is stochastic gradient descent, and it fits in a single line. Everything hard, everything genuinely interesting, is hiding inside step 3, the backward pass. So let us look at the very first thing that flows backward through it. When the error starts its journey backward, what is the first number it carries? It is the gradient of the loss with respect to the score, and for our head, it is astonishingly clean. Here is the whole grad method. It returns exactly one number, the sigmoid of the logit minus the true label. But the sigmoid of the logit is just the prediction. So the entire quantity is the prediction minus the target, nothing more.
So the gradient is literally just how wrong we were. That feels too simple to be doing real work.
It really is that simple, and it is no accident. Prediction minus target has a name, the residual. Think about what it does. When the prediction matches the target, the residual is 0 and no correction flows at all. The model is already right, so leave it alone. When the prediction is wildly off, the residual is large, and a strong correction flows. The size of the mistake is exactly the size of the fix. That is the machine correcting itself. And here is the quiet miracle. This same shape, prediction minus target, is the gradient for every well-matched loss in the library. The classifier, the counter, the real valued predictor. Swap the head, and the residual is still just prediction minus target. That is not a lucky pattern. It is what it means for a loss and its output to be matched, and later episodes lean on it hard. It is the seed the entire series grows from. It is also the mechanics underneath inductive biases, episode 1. The network computes numbers, and the loss decides their meaning by handing back this one number that says which way to move. So we have the seed, but notice what we have quietly assumed. We trusted that the backward pass, once it runs, delivers the correct gradient for every weight. We have not proven that. Next episode, we earn it. We derive the backward pass by hand, layer by layer, and then, this is the standing promise of the series. We never trust a gradient we did not check. We put it up against the raw numbers and prove it, right on screen. Enough on the page, let us watch the thing actually learn. These are the 2 toy blobs from the demo, one class of points down in this corner, one class up in that one. We want a line that cleanly separates them. The entire setup is a single line of code, a network built from one linear layer with 2 inputs and 1 output. And the sigmoid head, then trained for 80 passes over the data at a gentle learning rate. For the replay, I start it from a deliberately bad line, so the boundary begins at a careless angle, slicing right through both clouds and getting nearly everything wrong.
So while it trains, what am I actually watching move?
Keep your eye on the boundary line. Each pass, every point pays its residual, every weight takes its small nudge, and the line responds. Watch it now. The boundary pivots and slides, sweeping across the plane until the 2 clouds settle onto opposite sides of it. And follow the number in the corner, the loss. It falls as the line finds its place. When the boundary stops drifting, the loss has flattened out, and the training is essentially done. And that is a neural network, trained from nothing. In pure Python, you could have written yourself. One linear unit, one head, a 4-step loop, forward loss, backward step. And the single quantity that set everything in motion was the residual, the prediction minus the target. We built every piece but one. We assumed, without proof, that the backward pass hands us the right gradient. Next episode, we stop assuming. We derive that backward pass by hand and check it against the numbers, because from here on, in this series, we never trust a gradient we did not check.